Alright, so I'm sorry if this makes you sick, but here's a first-person view of the rover. What do you think, Max? Alright, so this is a test of the rover. Actually, I pulled it out of storage. Just going to go ahead and boot it up. Oh. Derp. Router is booting. BB-8 is booting. I've already booted the Raspberry Pi, and let me pull up. Okay, so I'm ready to run this whenever. Alright. Alright, so this is a demonstration of my Beaglebone Black BB-8 rover. This is just the carriage by itself. And right now it's booted up and running. You can watch me here. And basically it's just a test to show that it works, and it's probably going to be the last video I make of it before I take it apart, because I am not very happy with the way it works inside the sphere, as you'll see later. So let's put it in the sphere and see how that is. Alright, so this unfortunately is the part where things get difficult. The sphere there is a 10-ply fiberglass layup. It weighs very little, how about that? And you can kind of see the fibers through some of the scratches in the paint. And this is Plasti-Dip on the outside. I wanted to make it white, but it's one of the problems with the whole BB-8 theory. It gets dirty real quick, so you can see. It's this is minimal use. It's just full of dirt all the time because it's rolling across the ground. Second part of the problem here is I have to get this carriage into that sphere every time you want to get to the mechanism. So, kind of got a method here where I squeeze it. This is an Easter egg. Think of it like an Easter egg. So you have to pop the lip, and there's this. Get the crud out of there. Alright, so you can see the fiberglass a little better on the inside here. I laid this up around a stainless sphere, and unfortunately it had fittings at both ends because it was a pressure vessel, and so there's Bondo in here to flushing it out. Then I used some tape, some fiberglass tape, to make that joint. So it's not perfectly round, but it's pretty close. Then you gotta get the thing closed again. These are old tires. They're old inner tubes off of bikes. And they do pretty well keeping traction on the inside of the sphere. You can see that the follower wheels are just perfect, and they do slide rotationally because they're on the wheels. So when this thing turns in its place, you see there, it does pretty well. You see some slippage from the high points where the wheels are rubbing. So let's going back, forward. And then we'll close it up and I'll show you how it works. So now for the hard part. This line has to line up with this line here. I usually put that in first. And you have to find the close point. It's tricky because it wants to eggshell on you. And that's how you seal it up. And signal loss is not terrible, but it's not great either. See if I can get a better shot here. Alright, so when I move it, you can't actually tell the direction of the carriage. Or you can tell the carriage is pointing that direction, roughly. When you go backwards, you can tell the thing is not staying stationary inside, it's losing traction. But you can kind of estimate where it is. So it's best to make gradual turns here. Otherwise, there's no way to tell where the heck you are. There we go. And I'll roll it off the edge here for you. So now we can try to back up this edge, but no guarantees. Oh. Oh, that's not it. All that cracking is just gravel. It weighs enough that it sounds pretty nasty. Now I gotta find its orientation again. There we go. So you can see it doesn't go up edges well at all. And that's slipping. So you can hear it trying to move. The counterweight of the batteries is enough that it can't turn over. But if you try to get up, it's not possible. I've tried rocking before. Maximum lip I've been able to get up, I think, is about 1 inch. So there's one of the problems with this design. You can tell when the sphere rotates, it throws off my perception of where the carriage is inside. So it's not an inherently stable system at all, given that I'm the only feedback in there. For instance, if I had a gyro with a Kalman filter or something in there, or a compass is better. Be able to tell from the screen which direction I'm pointing to some degree, but not so much right now. So, if as kids you guys ever had those funny little squirrel looking toys that just sort of roll around and they have the tail, that's pretty much what this is. Alright, so now you're probably wondering what's going on inside this thing. So I'll show you. Main power switch is here. Unfortunately, I have no way of shutting this thing off without hooking up a mouse and controlling it. Basically, I could VPN into it, but I'm not going to spend the time to do that. So the router has this top shield. Just elevates the router up a little bit, keeps it away from metal. I have 4 screws holding the shield on. And the shield also serves as sort of a FOD control thing. If I have dirt floating around inside the sphere, it just keeps it away from the beagle bone, from the beagle bone black, from the USB ports and motor controller and all that stuff. These screws tie into a piece of T-slot, 80/20 aluminum, so it's a 1 inch by 1 inch piece of, or 1 inch by 2 inch piece of extrusion. The plastic shield on the bottom keeps the batteries in, and it's bolted in the same way. So, the router has a 12-volt power supply, the beagle bone and the USB hub take 5 volts. So let's get you closer. Alright, so this is a buck converter. It's adjustable, but I've configured it to output 12 point something volts, something slightly high. It takes 24 volts in and 12 volts out. It supplies the router with up to, I think it was 4 amps. I don't remember for sure. The fan is coupled with this power supply, which has an auxiliary fan port, and the fan just keeps both power supplies cool. The lower power supply is a 5-volt buck converter, very similar, and it supplies the beagle bone and the USB hub with 5 volts. Motor controller is powered directly off the 24-volt battery. Now the USB port here on the motor controller runs to the hub, because the BeagleBone Black, in its infinite wisdom, only has one USB port, which was right there. This is the HDMI port for your display, and it's a micro, I think, or mini HDMI port, which I hate, so I would switch this with a Raspberry Pi if I were to do this again. So there's your 5-volt in, 5-volt in for the USB hub. I have a Logitech wireless mouse and keyboard attached to this thing. There's a USB dongle for storage. That's where I keep the files. And then the USB, of course, runs to the hub so that I can run the motor controller and those other things off of the BeagleBone Black. That USB hub was kind of an afterthought because I didn't really remember that the BeagleBone Black only has one USB port, which stinks. Unfortunately, or fortunately, the Raspberry Pi has 4, so that's a major upgrade on the other client side. These are the Omni wheels I was talking about. They just bolt into the T-slot extrusion as well. It's just sort of jerry-rigged together. These I got lucky with. Turns out they are at the perfect length. Alright, so I've taken off one wheel to show you what's going on here. It's an ugly wheel, I get it. It's just a bunch of plywood discs that have been wood lathed down into the profile of the sphere. And then there's a hub, and it attaches via a set screw to the shaft, which has a flat on it. The motors, I'm not going to show you, it's a pain in the neck to take apart the whole thing. The motors are gigantic. They're geared brushed DC motors, and I think they have some ridiculous step down of like 100 to 1 or 200 to 1. They're meant for segways, so they have so much torque that I could make this work with anything in terms of weight and friction. These are the batteries. They're nickel metal hydride 24-volt batteries. You can see there. There's two of them because I needed weight, so I decided that an extra run time would be great to have. These are 5,000 milliamp hours, so we have a total of 10,000 milliamp hours, or 10 amp hours worth of power on this thing, which means that if it only draws, I would say it probably only draws around 5 amps peak. So in the event you're running this thing all the time, in the worst conditions possible, that would be 10 amp hours divided by 5 amps, which is 2 hours. At best, this thing, I know this thing can run about half a day. I've done it before, just having fun with it. In fact, this thing is more fun to run without the shell. And if I were to pull these idlers down, this would be an incredibly fun little robot to have to bring to robotics club meetings and stuff. And it's also, given the fact that it's so compact, it fits through doorways. Its low center of gravity with the batteries makes this thing very sturdy, stable. And without the shell, it can go up and over bumps and stuff, but it needs to have bigger wheels to do so. Slightly bigger wheels. What I've done is just coupled the two batteries together using a splitter, and that's not great practice, but it allows me to charge both batteries at once. As long as they don't overheat, everything's good. They're pretty good batteries, so I trust them enough to do that. Main power then just goes straight to the switch, which you can see there. Alright, so you might be wondering what's going on inside the rover itself on board the BeagleBone Black computer. So here's a quick summary. This is called joystick motor. It's because I'm using an older version to write this code. Originally I had the joystick directly controlling the motor controller. So whenever you see a joystick in here, it's just left over. So the onboard, well, the startup script looks something like this. You'll have a shell script executable that is called by the bash.rc file as part of Debian operating system. So when you go into bash.rc at the very bottom, you'll go and call this. You call a script either this script, this .joystick motor script, or you'll call another script which has other functionality on the desktop. This just changes directories to the desktop from the root, and then sudo./joystick motor executes that joystick motor executable. This whole script here I'm about to show you is compiled using G++, which is a compiler built for Linux. Works really well. I like it because it's simple. You don't have to go try to track down file paths, compiler paths in Genie, for instance. Alright, so let's start looking at this code. I've included some of the important libraries here. For instance, there's socket.h, which is for your TCP/IP communications for server-client network. libUSB, you need that for the motor controller control over USB. Math.h, obviously for mapping things. Joystick is only on the client side, it's just here because it's left over. What I've done here is I've defined pi. I've also defined the left and right motors as 0 and 1 as preprocessor definitions. This is because you have to alternate which motors you write instructions to. For instance, I cannot tell the RoboClaw to write duty cycles to both the left and right motor at the same time. So I have to basically have a switch statement that says write this information to the left motor, increment, okay, now write to the right motor. This CRCX modem is a CRC checksum, which stands for something recursive checksum, and it's a 16-bit checksum that is required by the RoboClaw. Now it's ion motion RoboClaw motor controller over USB. It's something you have to send with the command in order for it to verify before it modifies system parameters. This is just an error script. It tells it to exit whenever there's an error, especially when connecting between the server and client. This is what I would modify if I wanted it to continuously pull after a client has disconnected in order to reconnect the client later. But I don't have plans to do this yet. So here's our main function. We're initializing the server, the sockFD, new sockFD port number, and the sock length and client length are items that are they define the server location and the client location or client address. And the buffer is used to hold data from the client. The socket address and the client address, they're combined in the struct. And so next we have to initialize USB. So here you can see there's this unsigned character, this 5 characters or 5 bytes of data that I am using to store data to send back to the client. I have another one here as data received to receive from the client. Then I have actually, I'm pretty sure I'm using this one as the receiver, receiving data, not the sent data. There's a CRC placeholder which will take the place of the checksum until it's actually calculated. You have to get the device handle for the USB device, which we'll see initialized down below, or we'll see the device identified and stored later below. It's just a device pointer. And then these duty cycles are used for mapping the duty cycles when we send to the USB over USB to the motor controller. Alright, so when we initialize the server, a lot of stuff here I don't understand. I'm pulling from the API for the socket library, but essentially it tells it to open a socket locally at port number 2000, so on the BeagleBone Black, port number 2000 at IP address 192.168.1.30 will be open and awaiting a connection from a client via the 192.168.1.29 router. But you never have to specify that because the router does that information, or does that thinking for you. It manages it for you because it's connected over Ethernet. And it's a link. It exists, and this becomes a server because it initiates the conversation. So this is the listen functionality. It basically holds it open and waits until it gets a client. This is where you assign the client identifier, and it binds it. So it makes sure that the client is held onto by the server. So when we see things like, where is it? This listen, I believe it listens indefinitely. That's the way I've set it up. That's why on startup, the server, BeagleBone Black, will wait forever until I get a client that connects. So now we have to initialize the USB connection. This is the important part here. This is the vendor ID and the product ID of the RoboClaw motor controller. You can obtain that information using LSUSB something. It gives you more information about the endpoint. So the vendor ID, product ID, and endpoint information tell you what you're connecting to, regardless of whether the devices are identical. I've never done it with two identical motor controllers, but supposedly it's doable. So for instance, since I have 7 ports on my USB hub, I should be able to control 14 motors via 7 different motor controllers. But I've never tried it, and I think it would get pretty messy pretty quickly. Especially if you accidentally rearrange some cables, you have to make sure those endpoints are the same as the way you set them. Because I don't think they're static. I think they're dependent on physically the connection via USB. It gives me some warnings or some information if they connect correctly, and then we have to claim the interface so that nothing else can connect to that motor controller. And there's an infinite loop, which allows me to continuously update the duty cycles of the motor controllers as I get information from the client. So here is reading information. We're reading bytes, up to 256 bytes from the client, and we're storing it into the buffer that we've created before. This is just debugging information, and as long as the size, or here we're just sending back our confirmation to the client that says basically we've gotten your message, and the client can use that information to verify, okay, we sent it, and this just verifies that it was written. So now we take that duty cycle information that we got in buffer, that's where it's stored. It's a series of 5 bytes. We obtain the first 2 bytes. The remaining 3 bytes are part of a checksum. I don't think I'm using it actually on the server side. And we're taking the buffer item 0 and item 1. We're mapping them through sort of it's like a linear shift. So it subtracts the unsigned byte 0 to 256 range by 128, so that we get values between negative 127 or negative 128 and positive 128. And then we throw that into a data struct, data 0, 1, and 2. So those first 3 bytes are going to be sent over USB. Same thing goes for right motor. This is that switch statement that consistently updates left and right motors. And then what we do is we get the CRC, the something recursive checksum, using this above function that I showed you before, right here. And then that 16-bit information gets stacked into 2 sets of 8 bits, which are basically 2 bytes of information. Those 2 bytes are then they're stored into items 3 and 4 of this data structure, data array. Then we do a bulk transfer over USB at the device handle, which is the USB connection to the RoboClaw. We specify the endpoint of it, and then we throw the data structure, the array in there. There's a total of 5 bytes being sent, and then it returns, as part of this bulk transfer, the libUSB will return at this pointer, at this data location. I believe this is how many bytes were written successfully. So what we do is we check to make sure that, 1, the returned Boolean, I think it's a Boolean, is correct, and that we did successfully write 5 bytes over USB to the motor controller. This read from USB motor controller functionality exists, and I think it is actually reading, but I don't do anything with the information. because I never quite figured it out, but I don't need it yet. This would be if you wanted to have a feedback control circuit going on. You could read encoder information from the motor controller and use it to create a closed loop system. You could also read current, like amperes being pumped to the motors, things like that. Here's the end of the infinite loop. So this is where things recirculate, gets more data from the client. It throws it into a duty cycle conversion. It then sends it over USB, and then it tries to read, but we don't need that. And once that breaks, i.e. once the client severs the connection, that error function is called and it breaks out of the infinite loop. Then we release the USB interface, we release the USB device, and we terminate the server. Now on the client side, this one is on the Raspberry Pi, for instance. You could have a startup script as well, which would look very similar to what we saw on the server, but it needs to wait for the connection to the router, which is on board the server, or on board the rover. So I never really got that to work, because you have to wait for a server connection, or for a router connection before it works. I compiled this one in G++ as well. The important one here is joystick.h, and also, as before, the socket.h. Socket allows you to do the sending to the server. I defined pi. I believe that's part of a mapping thing I did. And then there's the error function again. We don't need the CRC checksum on this one since there's no USB communication. The joystick is controlled over USB, but by its own library. Main function, we initialize the joystick. This is the joystick device, and then we have stuff that I've pulled from the API. I don't understand why they made it so complicated, but basically there's a pointer to store the state of all the buttons and all the axes. There's this raw duty cycle that I've initialized. There's let's see here, this is the client information, so similar to the server side, and a server pointer. We have to initialize the joystick, so here's where we will pull the most current joystick, or the first joystick which is connected, which is dev input JS0. So regardless of whether you have 5 joysticks plugged into your computer, it's only going to pull the first one. So that's one potential issue. Then it populates the list with the number of axes, number of buttons, the name of the joystick. We can get the let's see here, this populates the axis array and button array, I believe, with the pointers to each axis and button. Can't quite remember. And it lists them. That happens at startup. Here we're initializing the server. There's our buffer for sending information to the server. We have to be on the same port number, 2000. And then here's the important part. We need to get the host by name, which is the Beaglebone Black TCP/IP address, which is 192.168.1.30. If you put the router address in here, the router doesn't know what to do with it. You can ping the router, you can ping the Beaglebone. Both will be pinged, but you have to identify the actual server, not the server's router. See here, next, it's going to try to identify, it's trying to connect, so the server has to be in that holding pattern and listening for the client before it connects. This is where it gets the port number and throws it into the server address struct. Then you got a connection at the socket address, and that's complete. You're going to have to look at the API for a better explanation of that. So here we begin our infinite loop. We're first going to grab joystick information. This is where we read from the joystick object at the joystick pointer location the current state of the joystick, be it
the axes or the buttons states. So axis array will contain the values of the axes. The button array will contain the values of the buttons. We then have to scale it, so we pull in the axis data. We're not concerned with the button data right now. And what I end up doing is I scale it so that I get only unsigned characters, so I can send those over the server client connection much easier. So I get raw duty left, raw duty right, or duty right, and then I put those into a buffer, and that command buffer will be sent. So here you can see I actually have a second buffer. Buffer here is for receiving from the server. That's that acknowledgement command, or the acknowledgement buffer. And then we have command buffer, which is written to the socket. There's 5 bytes being sent. I don't know why I'm sending 5. In reality, I could just send 2. So there's 2 positions containing 2 unsigned bytes. Then it reads the response, and as long as we get a response, it is a successful write. So this just repeats forever and ever. It's just sending regardless of what the client or server sends back, and then we end the server here and we end the joystick connection there. So when the client gives up, or when we terminate it, it will terminate the loop on the server end. When we terminate the server end, the client has nothing to send to, and it'll send an error. So that seems to work pretty well. It's a little temperamental at times, but it seems to work. There are also, for instance, no faulty data checks, so there's no checksum in the server to client connection, so it could go potentially haywire. I'd like to fix that at some point. And that's a general overview of how the server to client connection works with joystick on one side, USB motor control on the other.